cover first the parasympathetic nervous system and then the sympathetic. And that's why today, inshallah, I'll try to cover cholinergic agonists and antagonists. Because you need to understand, so I hope that every slide, I'll explain it to you, and I hope that you are following with me. If you have any questions, don't worry about the time. If you are actually short of time, I'll try to find a solution. Either I'll record something for you or anything. But the most important is that you are following with the flow of the lectures. When we say cholinergic agonists and antagonists, I'll just revise 2 slides for you to remind you about the introductory lectures. The nervous system, as you have covered, is classified in your anatomy into 2 important components, which are the central nervous system and the peripheral nervous system, right? But if you are talking about body functions, then you need to classify it differently, and we need to classify it by, depending on the function, into a somatic and autonomic nervous system. And what is the somatic, basically, is the one that is involved, it's the one that you can control. It's the nervous system that you involved in the voluntary control of the skeletal muscles and locomotion. This is the thing that you can control yourself, but you are not in control of the speed of digestion of your meals. You're not in control of the heart rate. You're not in control of your blood pressure, isn't it? So these are the body functions, or the essential body functions, that are under the autonomic nervous system control. So this is the involuntary regulation of body functions. And you have covered that we have afferent neurons and we have efferent neurons. And the efferent neurons in the somatic is different from the autonomic. Most importantly, the autonomic nervous system, that we do have our anatomy and function divides the efferent neurons into 2. Okay, we have the first nerve cell, or we call the preganglionic neuron, and we do have the second nerve cell, what we call as the postganglionic neuron. Why? Because there is an autonomic ganglia in between, which is a collection of cell body outside the nervous system. So basically, the signal will be taken by 2 steps before it reaches the effector organ, whether it is a sweaty gland or a gastric gland or salivary glands or whatever, right? What is the situation in the somatic nervous system? Do we have like this mediation autonomic ganglia? No, it's a single myelinated fiber that travels from the CNS to the skeletal muscles, okay? So depending on this structure, which one do you think is working faster? Yes, okay. So the autonomic will take time, right? So if you and all this is for the purpose. If you see something, for example, dangerous and one wants to escape from, there is a fire and one wants to escape, you need to escape within seconds or minutes, صح? So you will do the voluntary control of your skeletal muscles very, very quickly. But if you eat a meal, for example, how long does it take you to digest that meal? This is the autonomic, صح? Yeah, so the regulation or the processes under the autonomic will take time accordingly. Now, this figure actually helps you when you study the autonomic nervous system, whether you're talking about parasympathetic or sympathetic. The first 2 rows that you can see are the classic representation of the cholinergic transmission or the parasympathetic nervous system, and the one next is the sympathetic nervous system. So these 2 are the classic representation for what is happening. But then you know that you have some exceptions to the rule, right? Either different neurotransmitter or something, there must be something that's considered as an exception from the normal circumstances, okay? When we want, in the parasympathetic nervous system, let's take it for example, if I want to classify that neuron, I will classify it based on the fact, where is it located in relation to the autonomic ganglia? Is it before, okay, where the cell body actually originates from the CNS, or is it actually coming after the autonomic ganglia, where the cell body is there and the neurons are, or the axon are traveling away from it? So we can say preganglionic or postganglionic, okay? And then depending on the anatomy, does it belong to the sympathetic or parasympathetic nervous system? And then what is the neurotransmitter that it uses? You know that what types of neurotransmitter that we have for the transmission of the signal? We have acetylcholine. And if the neuron is using acetylcholine, what am I going to call it? Cholinergic neuron, yes. And if the signal is being delivered by adrenaline or epinephrine and norepinephrine, we will call them adrenergic neurons, okay? Okay, so based on this knowledge, what is that? This is a preganglionic, parasympathetic, cholinergic because it releases acetylcholine. And what is that? Postganglionic, parasympathetic, cholinergic neuron. Okay, that's the basic thing in parasympathetic nervous system. What's the basic thing in the sympathetic nervous system? I have a short preganglionic, sympathetic, cholinergic neuron because it releases acetylcholine to the autonomic ganglia. And what is that? Postganglionic sympathetic and releases epinephrine, so we call it adrenergic. Okay, what is the exception here? Sweaty glands. What is the exception, the sweaty glands? Yeah, so the postganglionic sympathetic neurons, they do not release adrenaline, they release actually acetylcholine, right? So that's why sweaty glands is one of the organs that will be sort of stimulated by both systems, okay? Whether you're talking about sympathetic stimulation, you will actually sweat quite a lot, or there is some sweating response. If you're talking about availability of acetylcholine, similar molecules, then again, they are going to work on the sweaty glands because this is their target. That's the exception, sweaty glands. What is the exception that we have in the renal blood vessels?
Can you use the pointer in the computer because of the people so they can't see actually.
Okay, طيب, okay. What is the exception in the renal blood vessels? Yeah, the postganglionic sympathetic neurons are using dopamine, which is another neurotransmitter that belongs to the sympathetic nervous system. What about the adrenal medulla? Yes, so basically they would not have a distinct post-ganglionic neurons, somewhere. They will secrete immediately. You can consider that the post-ganglionic neurons are within the adrenal itself, so they will secrete the epinephrine or norepinephrine directly to the bloodstream. Okay, so good. So you are quite prepared to progress. Now, where are the cholinergic neurons that I will be talking about? All preganglionic, whether I'm talking about sympathetic or parasympathetic, are actually cholinergic because they release acetylcholine. Okay, what else? All the postganglionic, parasympathetic fibers are again, they are cholinergic. And remember sweaty glands, yeah? Although that they are actually having sympathetic supply and it's only sympathetic supply that they're receiving, but the neurotransmitter that actually acts on them is acetylcholine. Do we have cholinergic neurons somewhere else? Yeah, the somatic nervous system actually. That we said, a single myelinated fiber that comes from the CNS back to the skeletal muscle, it will release what at the motor end plate? Acetylcholine. So don't forget that in our lectures, somehow somatic might be involved or skeletal muscles might be involved with us. What about cholinergic neurons in the CNS? Cerebral cortex, okay? We still have cholinergic neurons in there, okay? And we do have, actually, they are both muscarinic as well as nicotinic with different subtypes. And acetylcholine centrally is very important neurotransmitter, it's very important excitatory, and it is important for us to learn. It's important to have memory, for the reward process itself. So it's very, very important neurotransmitter for learning. What happens if somebody has got degeneration of those cholinergic neurons centrally or do not have adequate acetylcholine to work on them? Have you heard about Alzheimer's dementia? Okay, so the known so far pathogenesis of Alzheimer's dementia that there is some degeneration in the cholinergic neurons centrally. If we need acetylcholine to learn and to memorize and to educate ourselves and be alert, unfortunately, individuals with dementia will lose that. They are not actually remembering and they cannot learn new information. Okay, acetylcholine now. There are 6 processes. I think you covered these with Dr. Dilip. Yeah, so we have synthesis, storage, release. So I'll go over the key component. Choline combines with acetylcholine, okay, in the presynaptic neuron itself, and then with the help of the enzyme choline acetyltransferase. This is the enzyme that we need in order to make choline. And where do we get choline from? It's an important component in the cell membrane itself, in sphingomyelin and phosphatidylcholine. Okay, and acetyl-CoA is an important metabolic molecule involved in metabolism. So we use this enzyme in order to make it. Once we make it, we store it in synaptic vesicles. And it is ready in the presynaptic neuron or cholinergic neuron that we're talking about. Once action potential comes, what will happen? With the calcium entry, it will cause fusion of the synaptic vesicles, as you can see here, with the cell membrane, and accordingly it will release acetylcholine to go and bind with its postsynaptic receptors. Okay? Now, there is actually a certain process important, or there is a drug that I would like to talk about before we continue, which is botulinum toxin. You have taken in your microbiology a bacteria called Clostridium botulinum and the disease botulism. Okay, this is why it causes advanced muscle weakness and paralysis and ptosis and diplopia and difficulty in all of that. Yeah, because the toxin that is produces, which is the botulinum toxin, can cause, it interferes with acetylcholine release from the cholinergic neurons, okay, at the motor end plate. Okay, we're talking about somatic now. Okay, so how does that? Yeah, some people trying to investigate that there is a certain protein called SNAP, or abbreviated as SNAP. You don't have to worry about the mechanism. Just know that it interferes with acetylcholine release, because this is SNAP 25 is an important protein that helps with the fusion of the vesicles with the cell membrane to release acetylcholine. So basically, they will go once you that then neurotoxin will go inside, will undergo internalization, go to the cytoplasm, and then cause a cleavage of that protein, interfere with it, and will not be able to cause this fusion of the vesicles with the cell membrane and releasing acetylcholine. So we are somehow with the botulinum toxin interfering with the release of acetylcholine. Okay, so knowing that, in 1989 they started to use botulinum toxin after some purification for some therapeutic purposes. Whenever you have a case of a certain or increased muscle contractility or severe sort of exaggerated response than what you need, okay, then you can use botulinum toxin after its purification. And this is Botox, basically. So the first indication for it is strabismus. Do you see this, strabismus? What is the problem here? Where is the problem? In the right eye or left eye? In the right eye. You see the right eye is a little bit crossed. It's not, the strabismus means it's a lack of proper alignment between the two eyes when you look into a certain direction, okay? If I'm looking that direction, they should both looking, and the sort of, my eyes are aligned together and the same position, okay? It's not like this one. He's looking straight forward, but the right eye is looking as if that there is an object to the left. And this is because of disbalance between the power of the muscles that are controlling the orbit, okay? So here there must be, this muscle might be stronger than the lateral. Say, for example, internal rectus or lateral rectus, okay? So one of them, if it is stronger than the other, it's going to pull the eye. It's not, the eye will not be in the center. This has got ophthalmic visual problems as well as cosmetic, okay? So they start to inject the muscle with a little bit of Botox, okay? And then it becomes weaker, balances the other muscle, and then the position of the eye becomes correct. واضح شباب؟ So that's strabismus. The second indication is blepharospasm. Blepharospasm, sometimes there are certain individuals and unknown, sometimes it's a benign condition where there is involuntary closure of the eye. They cannot just open their eyes because the orbital muscles are actually contracting too much. So they need to inject Botox around these muscles to relax and open up the eyes. And then it started to be used for hyperhidrosis, excessive sweating. You know that sweaty glands, we know that it receives sympathetic supply only. But since it is using acetylcholine, then I can, in the armpit or in the palms and soles, wherever the excessive sweating is, we just can infiltrate that region with Botox. And the half-life is 3 to 4 months. So you will not need to take the injection before. And it's quite actually long-acting, so it's very, very, very good. And that saves a lot of money and invasive procedure. Migraine, again, it is the muscles are injected. Cosmetic, of course, but all of you, you know, sometimes any muscle that is contracting more than what is needed, then they can inject it with Botox and make it relax. Okay, back now to acetylcholine. The normal physiology, once it's released, will bind with receptors called muscarinic and nicotinic receptors. You know the names? Good. And once it binds, not only that, there is something called presynaptic receptors. What is that? That means the cholinergic neuron that is releasing a certain neurotransmitter, whether it's sympathetic or parasympathetic, that neurotransmitter will go to a postsynaptic receptors. This is what we know. Sometimes it goes back to the neuron that has released it. And there are certain receptors on the cell membrane, okay? Why it needs to go back? Because, it will tell the neuron, depending on the physiology and what is going on, if that neuron needs to release more or need to release less, or just continue with the same rate. But this is, subhanAllah, very, very beautiful mechanisms by which there is some regulation that happens. What is the enzyme responsible for acetylcholine degradation? Yes, okay. It will do that very quickly within 5 to 20 seconds. And then choline is being recycled and taken back by the neuron and can be used back. What is the difference between muscarinic receptors and nicotinic receptors? The muscarinic receptors are G protein coupled receptors. So there is a secondary messenger. Nicotinic receptors are ion channels. Yes. So which one again more fast? Nicotinic. And that actually complement what we have said about this difference between somatic, because somatic needs actually very quick ion channel opening and ion and electrolyte going inside the cell. Now you might be wondering why we call them muscarinic and why we call them nicotinic receptors. Huh? أيوة. She said that nicotinic receptors are activated by a substance called nicotine. صح? And muscarinic receptor is activated by a receptor called muscarine. A substance. Yes. So we call that receptor. طيب do I have muscarine and nicotine in my body? No. طيب why do I need to call that receptor after certain substances وأنا عندي acetylcholine? صح? Okay. The reason why is we have two reasons. When they were developed and when they were discovered. Okay. Muscarine is the first parasympathetic mimetic agent discovered on Earth by scientists. They were discovered in 1869, 18 سنة, okay, 69. So it was known to be a substance that activates some receptors somehow in the body, okay, and produces certain effects, okay? So muscarine, and where is muscarine is coming from? From toxic type of mushroom. This is where muscarine is coming from. And nicotine is the active ingredient from tobacco. And tobacco has been known since the 17th century, ages ago. People used to smoke some tobacco, okay? So knowing these substances, they were there and known before we discovered that these receptors are made, subhanAllah, to bind with acetylcholine. Look at the time when we discovered acetylcholine, 1929 only, right? So like maybe 100 years قبل ما نعرف إن أساساً these receptors were meant to interact with acetylcholine. So we discovered muscarine nicotine before acetylcholine, basically, okay? And look at the affinity here. This is important. They have stronger affinity than acetylcholine. So in case your body is being sort of intoxicated by nicotine, for example, it will fight or it will compete with your acetylcholine and it will get and it stimulates these receptors. Okay, so affinity again is an important issue, and for that reason we kept naming them muscarinic receptor and nicotinic receptor. واضح السبب؟ Okay, how many subtypes we have? Muscarinic, we have five: M1, M2, M3, different body organs. Like, for example, M2 in the heart, M3 in the glands. Okay, you do not need to worry about this subclassification. Nicotinic receptor, we have only two. One in the autonomic ganglia, we call them neuronal type, all right? And one, we have them in the, neuromuscular junction, or the motor endoplate. Excellent. So now, the cholinergic agonists, we have direct and we have indirect. When we say direct, they are basically structural analogs, or they are similar to acetylcholine, and that's why they will go to acetylcholine receptors and stimulate them, as simple as that, okay? And the indirect will do something different, but we'll see that. So when we say direct, we have two groups under that: esters of choline and alkaloids. When we say alkaloid, that means it's a naturally occurring chemical compound that has got a basic nitrogen atom. Most importantly, that alkaloids available in nature are highly lipid soluble. Okay, so that means the absorption from any route is going to be much easier, and you need smaller dose to achieve a certain therapeutic target. But when we say esters of choline, these are quaternary ammonium compounds. Any compound that has got quaternary ammonium compound, or the ammonium compound, is positively charged. Any positively charged substance is going to be less lipid soluble, okay? And accordingly, the absorption or availability for oral use or oral preparations are going to be less likely, or shorter half-life, or I have to give a bigger dose to achieve a certain therapeutic range. Under the esters of choline actually falls acetylcholine itself. We have